and we'll get started on our new material. So last week we started hypothesis testing, and that built on confidence intervals from the week before. Both of those are based off of our sampling distributions. Now remember the sampling distribution, let's just, for example, say for a population mean, it involved choosing a sample size. And we're just going to let that sample size be n. And selecting all possible samples of size n from the population. Finding the mean of those, of each sample. And then the sampling distribution is the mean, all those means of those samples. So it's literally sample means that are making up the distribution of the population mean. And of course, the characteristics of the sampling distribution the mean of the means was equal to the population mean. And the standard deviation of the means, remember that was sometimes called the standard error, was the population standard deviation divided by the square root of the sample size, n. And so with that very predictable set of characteristics for that sampling distribution, we were able to construct confidence intervals, do hypothesis testing and all that. Well, tonight we're going to go the next step. We're going to look at the sampling distribution for the difference of two population proportions. We're going to start off with the sampling distribution for two independent population means. So what this means is we've had two populations that are totally independent, no link, no overlap, no common elements between the populations. And we want to compare their means. So we're going to choose a sample from each of those populations. So we're going to choose sample sizes. N1 and N2, those are the sample sizes from each of the two populations, population 1 and population 2. Select all possible samples of those sizes from the appropriate population. So we select all possible samples of size N1 from population 1 and all possible samples of size N2 from population 2. And then we subtract N1 minus N2 for all possible combinations. So you can see there's a lot of possible samples of each size from each population, but then we have to take all possible combinations of those samples and find their differences. I should say not N1, but mu1, the mean of the sample for each one from the mean of the sample from population 1 minus the mean of the sample from population 2 for each of those possible combinations. So it's the difference of those sample means makes up the sampling distribution or the difference in population means. So these samples sample from population 1 has a size of N1, has a mean of X bar 1. I don't have a better way of writing it out without using the thing. It's just the X with the bar over the top and the 1. I'll draw it out in just a second. The standard deviation of S1. So technically, this here X bar 1 is X with a bar over it and a little subscript 1. I just don't have a convenient way of typing it out, so I will type out X bar 1 on the screen here for tonight. So the mean of the difference of sample means so this would be the mean U or mu of X bar 1 minus X bar 2 is going to equal simply the mean of X bar 1 minus the mean of X bar 2. I keep it equals instead of a dash, which is simply equal to the mean of mu1 minus mu2. So I can estimate the difference between the population means by just subtracting the sample means. Because on average, the difference of the sample means will equal the difference of the population means. A little bit trickier, though, is going to be the standard deviation of the difference of the means. And this one I am just going to draw out to make it a little simpler on me. So you've got sigma of X bar 1 minus X bar 2. So it's the standard deviation of the difference of those means is simply going to be the square root of sigma of X bar 1 squared plus sigma of X bar 2 squared. Now, we don't have those actual standard deviations, so we have to estimate those with the population standard deviation. So that's X or sigma 1 squared over N1. Remember, we have to use the population standard deviation divided by the sample size plus X2 squared over N2, the size of the sample from population 2. This is the heart of the variance or variation within these difference of means. Fortunately, we don't have to calculate it. The calculator is going to do that for us, but we do still want to understand where our test statistic comes from. So at this point, we are assuming we know both population means. Or not both population means, both population standard deviations. So that is, sigma 1 and sigma 2. If that's the case, then this is a z-test, and our test statistic z is going to equal the difference in our sample means minus the hypothesized difference in our population means divided by this standard error. So sigma 1 squared over N1 plus sigma 2 squared over N2, all in that square root. Well, that's not a pretty statistic to calculate, but let's take a look at an example here. Turn the page. There we go. So a city, oops. There we go. City A claims their mean hourly wage is higher than the neighboring city, city B. It is known that the standard deviation of wage in city A is $1.94 per hour, and in B is $2.04 per hour. Random sample of 60 workers from city A gives a mean of 17.82, and a random sample of 70 from city B gives a mean of 17.99. Now you might be looking at that saying, well, the wage in city B is higher, so we're done already. Not necessarily. Remember, it could be a little bit higher and still be within our tolerances, within the sampling errors. So we're going to test the claim of city A at alpha equals 0.10. So first of all, we need to come up with our hypotheses. The null hypothesis, cities A's claim is that their mean A is greater than mean for B. Now what we're going to do is we're going to word it as mean A minus mean B equals 0. Technically we mean greater than or equal to 0, but this strictly greater than just only works if the difference is 0. So in this case, it would have worked, but we want to be careful how we do that. The alternative hypothesis is then that the mean of A minus the mean of B is going to be less than 0. That's saying A would be less than B. Wording the hypotheses like that allows us to be very careful in how we construct a true sampling or hypothetical sampling distribution for this difference. Because we're not comparing the two means, we are constructing a sampling distribution for the difference of the two means. So it's technically more correct to have it worded the way we have it here right now. So since the alternative hypothesis is less than, we're going to reject on the lower tail, alpha of 0.10, and this is a z-test, so we can get our critical value there. Second distribution, inverse normal, 0.1, mean of 0, standard deviation of 1. We're just looking for a standard normal statistic here. We get negative 1.282. So Z critical here is a negative 1.282. So what that means, our rejection rules, for the critical value, we will reject the null hypothesis if the test statistic is less than a negative 1.282. For p-value, we will reject HO if the p-value is less than 0.10 of alpha. So now let's calculate our test statistic here. So we have Z equals the difference between our sample means. So that's going to be the 17.82 minus the 17.99 minus the hypothesized difference was 0 over the square root of standard deviation of 1.94 squared over the sample size from sample 1 of 60 plus standard deviation percent for city B, 2.04 squared over the sample size from city B of 70. And we can find that test statistic. Well, let's go to the calculator, see what we get. So on top, we have 17.82 minus 17.99 minus 0 gives us negative 0.17. Now we have to divide this by the square root of, now on the TI-84, we don't have to be all that careful entering this in. It works out fairly well. So we've got a 1.94 x squared divided by a sample size of 60 plus 2.04 x squared divided by a sample size of 70. And we hit enter. We get a negative 0.487 or 486, actually. We don't have to round up there, as our test statistic. Well, that is definitely not less than a negative 1.282. So according to our critical valued rejection rule, we failed to reject HO. Let's find our p-value. It'll give us the same conclusion, but let's find it. So our p-value is the probability that z is less than a negative 0.486. So we're going to simply go to the calculator. Second distribution, normal CDF. So less than will be from negative infinity to a negative 0.486. Mean of 0, standard deviation of 1. Giving us, oops, what do I have wrong in there? That should be put in a subtraction sign instead of a negative. That'll always cause an error. I get a 0.3135. So p-value of 0.3135, which is definitely not less than alpha of 0.10. So again, we failed to reject. So we failed to reject the null hypothesis here, which means even though in our sample, city B had a higher wage than city A, it wasn't a big enough difference that we could claim that we can reject city A's claim that they have the higher wage. Well, now that we've got this all sorted out by hand, let's take a look at how we do this on the TI-84. The one limitation of the calculator is the calculator does use that very poor form that we talked about, where we said over here that this is really the better form, statistically the more accurate form. But there was that form of, mu A is greater than mu B and mu A less than mu B. It's sloppy statistical form, but that's the form the calculator uses. And also the calculator only works if this value here is 0. That hypothesized difference in the null hypothesis is 0. Here it is, so we're okay. So let's go to the calculator. And we're going to go to stat, tests, and we have to go down to 2 sample z-tests. So option 3 there. We're using the statistics. The mean of sample 1 is 1.94. Mean of sample 2 is 2.04. Or sorry, the standard deviation of population 1 is 1.94. Standard deviation of population 2 is 2.04. The mean of sample 1 is 17.82. The mean of sample 2 is 17.99. Oops, sorry, the size of sample 2 is, or sample 1 goes in there, 60. The mean of sample 2 is the 17.99. The size of sample 2 is the 70. Okay, making sure I got them all entered in correctly. Now our alternative hypothesis is less than, so that is correct. And we hit calculate. And then we get the exact same test statistic, negative 0.486, and the exact, well, close to the exact same p-value of 0.3134. Instead, we had 3135. But it's the same thing. Either way, we rejected, or we failed to reject the null hypothesis. So we failed to reject HO, which means there is not sufficient evidence to refute City A's claim. So even though our sample showed a lower wage for City A, it's not low enough that we can say that City A's claim was wrong. What we're saying is the variation in the samples could be enough to explain the result we got. So since these numbers were essentially the same when we have enough evidence, okay, these numbers will always be the same between the calculator and what we did by hand. I was just showing you how to do it by hand so you've seen it, but mostly we're going to do it on the calculator because you can see it saved a lot of steps. But what we got here is the test statistic of negative 0.486 is not less than a negative 1.282, so we failed to reject. And also the p-value of 0.3135 is not less than alpha of 0.10, so that confirms that we failed to reject. And therefore, because we failed to reject, there's not sufficient evidence to say that City A's claim is wrong. We don't have to agree with it. We didn't prove it right. We just failed to get strong evidence against it. Well, this one assumed that we knew both population standard deviations. We had them both given here in the problem. Well, chances are if we know the population standard deviations, we're going to know the population means. So it's not very practical, especially with two populations, to assume that we're going to know the population standard deviations. So if that is the case, where we do not know the population standard deviations, now realistically, we only have to not know one of them for this to apply, but if we don't know one of them, chances are we don't know either of them. So that means we will use the t-distribution and we use S1 and S2, the sample standard deviations, in place of the population standard deviations. However, remember the t-distribution requires degrees of freedom. Here we have two samples. So how do we combine the size of the two samples to calculate degrees of freedom? Well, that is a really ugly formula. It's actually pretty tough to get totally correct. But our degrees of freedom are going to be sample 1 standard deviation squared over size of sample 1 plus sample 2 standard deviation squared over the size of sample 2, add those together and square it, over the size of sample, standard deviation of sample 1 squared over the size of sample 1, square that value, and divide by the size of sample 1 minus 1, plus the size of sample 2, or the standard deviation of sample 2 squared over the size of sample 2, square that difference, and divide by the degrees of freedom in sample 2, so the size of sample 2 minus 1. Yes, that formula is as ugly as it looks. So let's take a look at an example here of how we would do this. So here we have an ACT prep company. Claims their program increases ACT scores by at least 2 points. Independent random samples were taken. A sample of 45 students without the prep gives a mean of 19.2 and standard deviation of 2.7. A sample of 40 students with the prep gives a mean of, let's see, 20.9 and standard deviation of 2.4. Test the company's claim. Add alpha equals 0.05. So I see I got something in the chat here. Let's see what that is. How do I remember that formula? That formula, I don't even remember. I have it written down here. You can either, it will be on the formula sheet that is provided with your exam, with the final exam when you go to take it. Otherwise, I let the calculator do the work, and I'll show you how that works out here in just a little bit. Okay, so let's come up with our hypotheses. The null hypothesis, HO or H0. Well, first we should define our populations here. So I'm going to let mu1 be sample 1 be those with the prep, and sample 2 be those without prep. So H1 or the H naught or null hypothesis is going to be that the first mean minus the second mean is greater than or equal to 2. We're just going to say equals 2. So those with the prep minus those without the prep, 2 points higher. So the alternative then is that mu1 minus mu2 is less than 2. It's not at least 2 points higher. So our curve here, since the alternative is less than, it's going to be a lower tail, alpha of 0.05. So if we look that up, we're going to get a negative 1.645, I believe. Let me go check this out on the calculator. Second distribution, inverse normal, 0.05, mean of 0, standard deviation of 1. And there it is, negative 1.645. Okay, so that is our critical value. Oops, careful. I gotta be careful what I do here. I'm gonna step back. That is not our critical value because this has to be a t-score, not a z-score. So we have to find our degrees of freedom. So let's do our degrees of freedom here. Degrees of freedom are going to be standard deviation 1 of 2.7 or 2.4, sorry, squared over the sample size of 40 plus standard deviation of 2 of 2.7 squared over that sample size of 45. Close the parentheses and square that. That's going to be over our standard deviation from sample 1 of 2.4 squared over 40. That's squared over 40 minus 1 plus 2.7 squared over 45, all squared over 45 minus 1. Well, let's give this a shot here in the calculator. I say give this a shot because there's a lot of keystrokes here, and even I have actually had some issues at times getting this one going right. So we've got 2.4 squared divided by 40 plus 2.7 squared divided by 45, close parentheses and squared. So we get the numerator of 0.093636. On bottom, we have 2.4 squared divided by 40 squared divided by 40 minus 1, I'm just going to type in is 39, plus 2.7 squared divided by 45, close parentheses, squared divided by 45 minus 1 is just 44. We get 0.0011. So I have 0.093636 divided by 0.0011281469. And I get 82.99999. Now these always have to be rounded up. So that's 82 degrees or 83 degrees of freedom we're going to be looking at here. And so now I can find my critical value using the t-distribution. So second distributions, inverse t is option 4. My area is 0.05. Degrees of freedom is 83. And paste. So it's negative 1.663 is what we end up with there. So what that means is our rejection rule critical value, we will reject HO if the test statistic is less than negative 1.663. For the p-value, we will reject HO if the p-value is less than alpha of 0.05. So then let's go ahead and perform this test. Now, rather than doing this by hand and then coming back and doing it with the calculator, I'm just going to jump to doing this with the calculator. Finding the critical value and the rejection rule is really the only part that we have to do by hand. So on the calculator, go to stat, test, and the calculator does all that for us too, but sometimes you might be asked what the critical value is. You need to be able to find that. So we're going to go to option 4 here, 2-sample t-test. We're again working with statistics. X bar 1, that is the mean of our first sample. That was the 20.9. And the standard deviation of that sample was 2.4. That sample size was 40. X bar 2 was 19.2. Standard deviation of 2.7. And a sample size of 45. Our alternative hypothesis, once again, is going to be less than. Now, pooled here is a big question. If we were doing this calculation by hand, pooling the standard deviation or pooling the variance makes the calculation a lot easier. It avoids actually using that degree of freedom calculation. But since we're going to let the calculator do the work, we don't care if we have the easy way. So this will always be no on the calculator. We're going to make the calculator do it the hard way, but the more precise way. And then calculate. So you can see there's the degrees of freedom. 82.999 is exactly what we calculated. So that confirms that we did the right degree of freedom calculation. Test statistic of 3.07 and p-value of 0.9985. Well, what did we do wrong there? Well, what we did wrong was we forgot to account for the fact that the difference here is 2. This difference is not 0. Remember, we said the calculator always assumes that difference is 0. How do we account for that? We have to add 2 to the second sample mean. So instead of 19.2, it'll become 21.2. That makes up for that 2-point difference. So now that would be mu1 minus mu2 would equal 0 instead of 2. So let's go back to the calculator and make that change. So second, distributions. Oops, sorry, clear out that. Stat tests, 2 sample t-tests. And so sample 1 still has a mean of 20.9. Sample 2 is going to have a mean of 21.2. That was the 19.2 plus the difference of 2 that we hypothesized. Everything else stays the same. We just hit calculate, and now we get a much better result. So we get a test statistic of negative 0.542 and a p-value of 0.295. So t equals 0.542, p-value, come on, equals 0.29, basically. Well, what this is saying is both of those failed to reject. We're not, this was a negative here. We did not get less than negative 1.663, and we did not get a p-value of less than 0.05. So we failed to reject. The null hypothesis. Therefore, there is not sufficient evidence to disprove or even just argue with the company's claim. For the time being, we have to let their claim stand. There's not any evidence against, or not enough evidence against them. So those are the 2 tests for independent population means. The next test we want to look at is still looking at population means, but we're looking at not independent. It's what we call matched samples or paired sample tests. And what this requires is we either create 2 samples that have a logical link between them, like siblings. So the first member of the sample A would be one sibling. The first member of sample B would be the other sibling put into a different treatment. This is often done with twins, where if we have 2 twins, we have a set of twins that have the same medical condition. One twin gets one medical treatment, the other twin gets the other medical treatment. Assuming they're genetically identical, they should react similarly to the medications. So any difference between their reaction is due to the medication, not genetic differences. The problem is that there must be a logical reason to believe both elements of the pair should behave the same. You can't just take 2 people and say, hey, you're going to be the first people in each sample, and throw one in sample A, the other in sample B, unless we have some logical reason to put them together. You know, they're twins. That's a logical reason to put them together. Or we've tested them and they have identical DNA. That would be a reason to put them together. We have to have some reason to believe that they would have the same reaction under the same conditions, not just both being human or whatever the quality is. So what is more often done is a before and after treatment with the same sample. So we might test a group of employees to see how fast they can complete a task, and then give them a certain training and then test them again and see if they've got faster after the training. That'd be a before and after test. So what we're testing here is not the individual samples, the sample means, but the mean of the differences for each pair. So there's only one data set. So this is just going to be the test on the calculator is just going to be a simple t-test. So the example we're going to do here is football coach claims that his team outscored opponents by an average of at least 12 points per game over the last 5 seasons. A random sample of, what am I going to say, 12 games is selected from the last 5 seasons. The scores are given as this: the coaches and the other. So the scores are 45-14, 21-14, 35-24, 31-28, 28-21, 20-3, 34-24, 42-31, 41-28, 27-10, 20-14, and 18-20. So the last game was the only one of the random sample that they lost. So what we would do is we would calculate a score difference for each. For this first game, 45 minus 14 is 31 points. 21 minus 14 is 7. This will be 11, 3, 7, 17, 10, 11, 13, 17, 6. Now the score difference here would be a -2. They lost by 2. Now what we're really testing to see is if the mean of this set of differences is really at least 12. So our null hypothesis is going to be the mean difference. Mu d is at least 12. Now we're just going to put equals 12 here because that's how we word our null hypothesis, always equals to. The alternative, though, is that the mean difference will be the opposite, less than 12. And now we can go ahead and perform our test. Now, what I'm going to do here is I'm actually going to put these in the calculator. Should get the same differences we have. What I'm going to do is we talked last week about that input option here. Instead of stats of inputting the data, we're actually going to use the data here. So we're going to do stat, edit. So we're going to go to the list, and I'm going to clear out my lists. List 1 here is going to be the coaches' team scores. So I should put those all in, 45. Why is that not, my number lock not on? There we go. There we go, 45, 21, 35, 31, 38, 20, 34, 42, 41, 27, 20, and 18. So there's all 12 of those games. List 2 then will be the other team scores, making sure we get them matched up with the right home team score. So we've got,
Is 38 correct? Sorry, for list 1, should it be 28? I may be mistaken.
Yep, that should be 38 is correct for that.
Okay, sorry, thank you.
So 14, 14, 24, 28, 21, 3, 24, 31, 28, 10, 14, and 20. Now we need to come up with the differences. These lists don't matter. What we're testing is the difference between those scores. So we're actually going to go up and highlight L3 here. Notice we're not in the list. We're actually highlighting the title of the list. And what we're going to do is we're going to do second 1 minus second 2. That gives us the formula here, L1 minus L2. And when we hit enter, it's going to subtract those and give us the differences. And this should be the same set of differences that we just calculated on the whiteboard. And you look at them, they are the same. So now we're going to get out of here. We're going to do second quit. I was just kind of glancing to make sure they were all the same. Hit stat and test. And we're actually going to just do a simple t-test here. And we're going to do our input as data. So when I select that, notice my options change. My hypothesized difference here is 12 points. My list is actually an L3, so I'm going to do second 3 to change that to L3. Frequency, we always leave that as 1. The alternative hypothesis, again, is less than. And we hit calculate. We get a negative 1.03 for our test statistic and a 0.4600 as our p-value. We did not calculate the critical value of t here. But a p-value of 0.4600 is definitely not less than alpha. I guess I didn't put my alpha up there, but we were testing at alpha of 0.05. We fail to reject the null hypothesis again. Yeah, so this is going to test the coach's claim at 0.05. I should put up here. If we wanted that critical value, well, it's just going to be a bell curve, 0.05 on the lower end again, because this is less than again. But this is a t distribution, so it's 0.05. There are 12 scores, so it is 11 degrees of freedom. And you do that inverse t calculation. So second, distributions. Inverse t, 0.05, only 11 degrees of freedom this time. And we get a negative 1.796 is our critical value. So since the test statistic of t is not less than negative 1.796. Again, we fail to reject the null hypothesis.
I have a
Either way,
question.
we failed to reject. Yep, go ahead.
Isn't our p-value higher than the alpha?
Yes, it is. It is not less than.
Oh, not. I didn't pay attention to
If
the
it
not.
were less than alpha, we would reject the null hypothesis. Okay, so our last step. Now, for each of these, we could create a confidence interval. The confidence interval is just going to be right off the calculator. For this data set, it would be stat, test, and it would be just a option 8, a t interval. And we would use the data setting with whatever confidence level. If we did a 0.90 or whatever, 90% confidence level, we get our confidence interval there. So that's saying that with this sample that the mean score difference in scores is between 7.38 and 16.12. We could have done the same for the others, stat, test. They have special intervals though. We go down, it would be not just a Z interval or a T interval, but it would be a 2 sample Z interval or a 2 sample T interval. Like the ACT prep would be a 2 sample T interval. We'd input with the stats. Mean one is 20.9. Standard deviation one was 2.4. Sample size was 40. Now here, since we're doing the confidence interval, we do not have to do that adjustment. It was only for hypothesis testing that we had to do that adjustment to make the difference 0 for the null hypothesis rather than the difference of 2 in the null hypothesis. So here we will put in the actual mean of 19.2, standard deviation of 2.7, sample size of 45. Confidence level, let's just go with 90. Pooled, always no, we'll make the calculator do the hard work. We hit calculate, and there it's going to tell us that the difference is between 0.7798 and 2.620. Since the 2 is in that interval, it's possible that there is a difference of 2. So that would confirm our statement that we were unable to reject the null hypothesis there. So anyway, back here, there is one type of sampling distribution we still have to talk about. It is a sampling distribution for the difference of 2 population proportions. So again, we're taking 2 samples and we're finding their proportions and subtracting them. The mean difference of proportion is just going to be P1 minus P2, just the difference of the population proportions. The standard error and the proportions, or the standard deviation of the difference of the proportions. This one I'm going to go to drawing it out again. It's just the square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2, which looks pretty familiar. I'm just combining the 2 standard errors, same as a single standard error formula, but with both of them under there combined together. But we need to be able to estimate population proportion. So our combined estimate from the 2 samples for the population proportion. And that is simply going to be either N1 P1 plus N2 P2 over N1 plus N2, or N1 times P1 is just X1. That's the number of successes in the first sample. So X1 plus X2 over N1 plus N2 to estimate the population proportion from the sample proportions. So anyway, let's look at an example here. So we have a dean believes that sections of statistics that use an online homework manager have a higher pass rate than those that don't. So a random sample of, wow, there we go, of 250 from sections using online homework gives 203 that passed. A random sample of 230 from sections not using online homework manager gives 193 that pass. test the dean's belief at alpha equals 0.10 again. So our hypothesis, the null hypothesis is that P1 minus P2 equals 0, or that P1 minus P2 is going to be greater than or equal to 0, but we always write it as equals to. So the alternative would be that P1 minus P2 is going to be less than 0. Let's go ahead and put this in the calculator. So stat test, we have to go down a ways. We need to get to 2 stat or 2 proportion z test right here, 2 prop z test. We select that. Our first, we had 203 successes out of N1 was 250. Our second sample was 193 successes out of a sample size of 230. The alternative hypothesis, once again, was less than, so we can stick with that, and we hit calculate. Well, we get a test statistic of a negative 0.781 and a p-value of 0.217. We didn't find our critical value of z, but it is just a normal distribution, so I'm going to trust you guys can find a critical z here. But the p-value of 0.217, it says all we need to know. So since the p-value is not less than alpha, we fail to reject HO again. So there's not enough evidence to refute the dean's claim. Notice we didn't prove it, we didn't confirm it, we just failed to reject it or failed to refute the dean's claim. So this is, like I said, it's the next step in things of combining 2 populations. And this is really where things get useful, because in real data analysis, typically we are comparing one population to another. Drug testing, we're comparing one drug to another. So this is the reality of how things work. The first test that I feel is fairly useful outside of an academic classroom. So make sure you're careful with these. The hard part is wording the hypotheses, just like it was last week, getting the hypotheses worded correctly. If you get them backwards, of course, your result is backwards. With that, I guess I am going to, that's all we have for new material. Do you guys have any questions? Well, I'm sure several will come up throughout the week. So oops, go ahead, Maddie.
I forgot to ask at the beginning of class because I didn't have my notes.
Yep.
But from the previous chapter, I think is the p-value treated the same as the t-value when it comes to the null hypothesis?
Nope, the p-value never depends on the null hypothesis. P-value rejection rule.
I forget what was, I didn't know what was being treated the same as the t-value. I just couldn't distinguish if there was enough evidence or not for my theories or the hypothesis.
Okay, so the p-value rejection rule is always we'll reject HO if the p-value is less than alpha.
Mm-hmm.
The t-value, which is a test statistic, is the same as the z-value, which is just a different form of a test statistic.
Yeah.
Those both use the alternative hypothesis, H1 or HA, depending on what your textbook uses.
Yes. Okay.
So those are the 2 that go off of the alternative.
Okay. Because it changes depending if it's the null or alternative one.
But you always
Correct.
use the alternative to set, it's always the alternative to set the rejection rule.
Always the alternative. So
You always
thank
have the
you.
alternative to
Okay.
see whether it's less than or greater than or not equal to.
Thank you for that.
You bet.
So with the problems for this week, is there an easier way to tell what your null hypothesis and your alternative hypothesis is going to be? Like, can you go over that last question that you did again? Because I was more so trying to write it down. I always go back through the video, write everything back down.
The wording on, to get the hypothesis, the wording in the problem is very, very subtle. What you are trying to test always becomes the null hypothesis. What you would like to show, if there was something you would like to show, that always becomes the alternative hypothesis. Because the null hypothesis can never win. The null hypothesis just fails to lose when we fail to reject it. But it didn't win. We didn't prove it, right? We didn't affirm it. We just failed to throw it out. So if it's something we want, we don't want that to be the null hypothesis. If it's what we want to show, we want that to be the alternative hypothesis, so that we can reject the null, and then we're left with no other choice but to go with what we were hoping to prove. But here, you know, where it says test the dean's belief, that means the dean's belief becomes the null hypothesis. If we were asked, try to show that the dean is wrong, we would end up with the same hypotheses, because trying to show that the dean is wrong, well, this alternative hypothesis would be the dean being wrong. So what we are trying to show, what we would like to show, always becomes the alternative. What we're trying to test is the null. Like I said, I know it's very subtle, and even I sometimes will be working through a problem and have to go back and switch them because my answer didn't work out. It really, when you're looking at these type of contrived problems, it's really subtle in the wording, and sometimes in real life, you are performing the test, so you know what the goals of the test are, so you know how to set up the hypotheses. But when these academic problems like this, you have to try to figure out what it is they're trying to test and trying to prove.
Okay. And is there a way of knowing that you enter these in incorrectly? Because I know when you're taking the test, there may be 1 out of 7 parts. And if you get that first part wrong, then chances are you're going to get the other 6 wrong.
Unfortunately, the only way to know you entered them in incorrectly would be like, let me go back here. So like here, I got a t statistic of a negative 0.542. If I were to get a t statistic of a positive 0.542, that is the indication that I did the calculation correctly. I just switched the hypotheses.
So your t statistic, well, I don't want to confuse anyone. I was going to ask if your
Your
t
test,
statistic
your
should
test
always be
statistic or
negative.
your test statistic, so that's either the t value or the z value, would be the same number but opposite sign. That means you switched your hypotheses.
Oh, I see, because this is a left-tailed
Yep.
test. Okay.
Yeah, so here it would be the t statistic or the test statistic, or here, let's go back another one. Here it would be the z statistic because it's a z test.
Okay, I have to look at your syllabus to see what your office hours are for the week, so I can see if I can schedule some time with you. But okay.
Okay. Yeah, just send me an email. Let me know what you have for free times, and we can see if we can set up a time.
Okay. Awesome.
Any other questions? Well, like I said, I'm sure questions will come up throughout the week, so please don't hesitate to send me an email or use that ask a question button in Alex. I have to go in and check. For some of those have not been coming through to me. So if you don't get an answer within 24 hours from me, don't be afraid to send me an email telling me you asked a question in Alex, and I can go in and search and make sure I found those for you. Otherwise, you guys have a great week, and hopefully we'll see you all back here next Monday. Next Monday is our last lecture on new material. So also make sure you are prepped and signed up for the final exam. With that, you guys have a great week.
Thank you, sir.
You're welcome.